All right, here is some help on 1A if you were absent or need help, okay? So the first thing you're gonna do is you're gonna just graph this data, okay? So notice it doesn't start at 0, 0, okay? So 0, 6, so 5, 10, 15, 20, 25. So each of these is 5, so 0, 6 is gonna be like right there. A little hard to see. 1, 18, so let's see, that's 20, so a little under there. 2, 38, 25, 30, 35, 40, so like around there. 3, 66. Oh, this is very hard for me. 50, 55, 60, 65, 70, around there. Oops, come on. All right, 4, 102. Let's see, where's 100? 100, 102, maybe like there. And then 146. I guess I probably could have done this before I turned on the video. Oh, I think it's right there, but my eyes are bad. 46, and then 6, 198. So that's way up almost at 200. Okay? Erase these other little dots. All right, so here's what it is. So what you'll see is that this is not a line anymore, okay? Because if it were a line, then we would know that the cart or wheel, whatever is this, a cart is moving at a constant velocity, okay? But when it's rolling down a hill, we know that it's not doing that, all right? So that it is moving at a increasing velocity, okay? So if we go ahead and do the motion map here also, if you sort of just turn your paper, oops, that's not what we want. Okay, if you sort of just turn your paper, I'm not gonna do this just for time's sake on the video, okay, but you can basically just plot these same points, right, kind of just across whatever, okay? And don't forget, motion maps have arrows coming out of the dot, and then they go halfway to the next dot, okay? So this is what it should look like, and then you can finish that, okay? All right, so what you're gonna do is answer these questions first. So what is the physical significance of the slope of a position time graph? So just as before when we had a graph like this, we know the slope is the velocity, okay? Tells us both the speed and direction that the cart is moving. And in the old case, that was a line. We just found the slope, but now it's a curve, okay? So we have to treat it a little differently because it's not a single slope anymore because it's a curve. But still, the slope still tells us the velocity, okay? As time goes on in our graph, you can see down here, right? Like if I did a slope like in this part, it's a lot more shallow than it is in this part. Okay, so the slope of the graph is increasing. Slope of the x versus t graph is increasing. It's getting steeper. Getting steeper. Okay, getting steeper. All right, so if I know that the slope is velocity and the slope is increasing, therefore I can say the velocity is increasing, meaning this cart is getting faster, okay, as it rolls down the hill. Okay. All right. Okay. Now, that's kind of qualitatively how to explain it. Now we have to try to calculate the slope, right? Okay. So what we're going to do, I don't know if I could do this on the iPad. We're about to see. Okay. We're going to draw a line connecting 0 and 6. I think it'll straighten. Yes. Beautiful. Okay. All right. So if we draw this line connecting 0 and 6 and take the slope of it, that can give us some information. Okay. So if I do 2 points, that's going to be 198 centimeters minus 6 centimeters over 6 seconds minus 0 seconds, okay? And that's going to be what's called the average velocity. You can draw a little bar over it for average. Okay, so that's 192 over 6, which comes out to be 32, all right? So this velocity, 32 centimeters per second, tells the average velocity in the time interval 0 to 6 seconds, all right? Because it's not actually going 32 centimeters per second, right? Because we already said in the beginning, like down here, it's slower, and then up here, it's faster, right? So that slope doesn't tell us the actual speed, like at all the time. It's just on average, right? If it had been going a constant speed, or on average, it goes 32 centimeters per second, okay? All right, the next one we want to connect is 1 and, oh, that's not even the right kind of pen. Nope. Okay, we want to connect 1 and 5. Eek. Okay, so we're going to do the same thing with 1 and 5, okay? So the average velocity, don't even tell me my pen's already dead. Pen's already dead. Great. Okay, the average velocity between 1 and 5. Okay, so we're going to go 146 minus 18 centimeters, and then 5 minus 1 seconds. And as soon as my pen comes back to life, I will write it. 146 minus 18. Okay. All right, so you're going to have hopefully, 146 centimeters minus 18 centimeters, 5 seconds minus 1 second, and this also comes out to 32 centimeters per second. Okay, so that is now the average velocity, okay, between 1 and 5 seconds. Okay, so again, it's not actually going that speed the whole time, but just on average, that's how fast it would go. All right, then I can do 2 to 4 seconds is the next one, so there's that line. So that's going to be 102 minus 38. Okay, 102 centimeters minus 38 centimeters, 4 seconds minus 2 seconds, and this is also 32 centimeters per second, okay? This is now the average velocity from 2 to 4 seconds, okay? So what we're doing is we're kind of shrinking this time interval, right? And then eventually, it's going to be really hard to draw on here, okay? We're going to get what's called drawing a tangent line at 3 seconds, okay? So tangent on a circle, right, would mean that it only touches at one point. That's what a tangent to a circle is. So on a curve, a tangent to a curve would be just skating by and touching just at 3 seconds, but not crossing in at all, okay? So let's see if I can, this is going to be so bad. Oh, that's not good at all. That's not good at all. Now, can I move the whole thing? Oh, I can. Look at that. Okay. Pretty good. Okay. Well, no, a little further. Wow, this is really hard to do on here. Okay, there. Oh, that's not bad. Okay. All right. So at 3 seconds, I'm going to draw that tangent line that kind of skates by and just touches at 1 point. Okay. If I want to find the slope of that tangent line, what I need to do is I need to find, say, 2 places, right, where it looks like maybe pretty good. So see, those 2 points are actually pretty good crossing right through, and then figure out the slope between those 2 points, okay? And you can pick whatever 2 points work for yours, all right? But what should happen is this slope, once you do that, should come out to be about 32 centimeters per second, roughly. It's probably going to be a little bit off just because drawing the tangent line is rather difficult, okay? And so what that's telling us is it's only touching the graph at 3 seconds, okay? So when I compare all of these points, this is kind of what you write in the summary, right? When I compare all of these points, what do you notice about all 4 of these lines? Okay, the purple, the pink, the orange, and the green, these lines are parallel. Okay, so these lines are parallel, which tells me that all of these are denoting the same velocity because all of the slopes are 32 centimeters per second, okay? So on average, let's look at the purple line. On average, that velocity is 32 centimeters per second. But in the beginning, see this down here, the orange thing I did? This is not even close to being a slope of 32. And this one up here is way more than a slope of 32. So in the beginning, the cart is slower than 32 centimeters per second. And then by the end, it's faster than 32 centimeters per second. So on average, it's going 32 centimeters per second, okay? Same thing from 1 to 5, same thing from 2 to 4, okay? So what you want to do is you want to look at these intervals. What is special about these intervals? 0 to 6, 1 to 5, 2 to 4, and then a single point of 3, okay? So what we're doing is we're shrinking that time interval, okay? Because at some point, the velocity has to actually be 32 centimeters per second, right? Because if it's going to average out to 32, sometimes it's less, sometimes it's more. That's why it averages to 32. So that means at some moment, the actual velocity has to be 32 centimeters per second, okay? And in this scenario, that happens at 3 seconds, okay? Because you can see 3 seconds is the middle time from 0 to 6, 1 to 5, and 2 to 4. So the slope of this, what we call secant line, this is the one that connects inside the curve, okay? The slope of this secant line equals the slope of the tangent line, okay, at the middle time. All right, so what we're doing is we're trying to shrink that interval smaller and smaller. So 2 to 4, we go 2.5 to 3.5, 2.9 to 3.1, 2.99999, 3.00001, right? We can keep shrinking that interval tinier and tinier and tinier until we get right at 3 seconds, okay? And then that would be what we call the instantaneous velocity at 3 seconds, okay? All right, so let's summarize maybe down here, okay? So the big idea, all right, and this is what's gonna show up on quick quizzes and summatives and stuff, okay, is if you draw a secant line, okay, between 2 points and take the slope, okay, the slope of the secant line is the average velocity in that time interval. Okay, so I can do that for any time interval I want. I can find the average velocity. So like if I wanted to know like the average velocity from like 4 to 6 or whatever, I could just do a secant line there, or I could do a secant line there. I can do it wherever, okay? And it would tell me the average velocity in that time interval, okay? This value is equal to the instantaneous velocity at the middle time, don't say midpoint, the middle time of that interval, okay? So the slope of the secant line, all right, say this goes from 0 to 6 in this case, okay? The slope of this is the average velocity in the interval, which means it's also equal to the instantaneous velocity at the middle time, which in this case is 3 seconds, okay? You can also get that instantaneous velocity from the tangent line. That's a little harder usually. Secant line's a little easier, okay? So it doesn't always have to be 3 seconds, right? So if I had something like this, and I had some graph like this, and this is 10, and this is 0, okay? If I wanted to know the average velocity at 5 seconds, the middle time of 0 and 10, I could use this line, okay? If I wanted to know x versus t, whatever, say this goes 0, oh my gosh, this pencil is just working my nerves, okay? Say that if my interval's like 0 to 6 seconds, for example, now let's say 0 to 8 seconds, so it's a little bit different. 0 to 8 seconds, okay? And I wanted to know the velocity at 3 seconds, let's say. So say this goes 0 to 8. 1, 2, 3, 4, 5, 6, 7, 8. Okay, 0, 1, 2, 3, 4. What if I wanted to know the instantaneous velocity at 3 seconds? Okay, I have a couple choices. I could connect 2 and 4. That has 3 as the middle time. I could connect 1 and 5. That has 3 as the middle time. I could connect 0 and 6. That has 3 as the middle time. See how they're all parallel? I could use any of those time intervals at which the target time is the middle. That would give me the velocity at that point exactly, okay? Or I could draw the tangent line and find the slope of that, okay? All right, so hopefully that maybe helps a little bit, but we're gonna have to probably keep working on it.